Okay, so today we're going to take a look at continuing 12.1, so I'll call it 12.1 continued. We're going to specifically today talk about special right triangles. These notes will be fairly short. You've done all of this before, none of it's new. Yeah, if you write small. Special right triangles. There are two special right triangles that you've dealt with in the past. Those are the two we're dealing with here. Anybody remember what one of the special right triangles would be? And what kind of right triangles? We call them, we name these special right triangles based off the angles. 30, 60, 90 be one of them. Let's start with that. So a 30, 60, 90 right triangle. And really, here's what's true about all 30, 60, 90. Well, actually, I'll let you maybe answer that question. What is true about all 30, 60, 90 right triangles? Are they all congruent? Are they all the exact same size? No, they're not. But are they the same shape, regardless of how much you scale it up or down? Yes, we had a word for that in geometry. We would say that they're all, starts with an S. Anybody remember it? I think I heard it. Similar. They're all similar. And we had a similarity. There's a specific similarity theorem that we had that allowed us to know that. How do you know what's the theorem that tells you that those two triangles are in fact similar? Do you remember? We just called them with letters. It would be like SSS, but if you look at the picture that's drawn, I might remind you which one it is. Angle. It's an angle. Angle is one of our similarity theorems. If we have two angles in one triangle that are congruent to two angles in the other triangle, they're similar. All 30, 60, 90 triangles are similar. Now, let's see if you remember what it means to be similar. In order for two figures to be similar, their angles are congruent, but their sides are what? They don't have to be the same. They don't have to be congruent, but they do have to be, it's a long P word. Not parallel or parallelogram. Proportional. They have to be proportional, which means we can make proportions out of them. We can make ratios. Now, depending on your teacher, and maybe your teacher even showed you a few ways you can do these problems, but there's multiple ways you might have set this up. So let's look at a couple of those, and then we'll actually practice it. So you might have algebraically, like in terms of, if we look at this first picture, there's a hypotenuse, and then there's two legs. The one leg is shorter than the other. The short one is opposite the 30-degree angle. That will always be the case. Sometimes we call it the short leg, but let's call that x. If the length of that is x, do you remember what the hypotenuse would be? Let me do it this way. Let me show you that if I reflected that triangle across that vertical side, sorry, it's not a very good drawing, but if I reflected it, what kind of triangle is that? It's an equilateral triangle. This side down here would be x. So what is the full bottom side? 2x, because you'd have an x plus another x. What's this side over here in the upper left? 2x also. What would this side over here be? 2x. Now I can go back and erase that. I can erase that and look at the triangle itself. And I know that if the short leg is x, the hypotenuse is 2x. I can make that a little more bold. Let me just try that over again. So if the short leg is x, the hypotenuse is 2x. What is the long leg? Anybody remember? It's x square root of 3. So you might have seen it like that with x's, or you might have seen it where instead of x, they put a 1 down there. Then what would the hypotenuse be? 2. What would the long leg be? Square root of 3. So you probably had something like that in geometry. Maybe they even wrote rules. Maybe you'd say, oh, if I know the short leg is whatever, the hypotenuse is just 2 times whatever the short leg is. I'll abbreviate short leg as SL. And then maybe you'd say, oh, the long leg is equal to the short leg times the square root of 3. Maybe you had some kind of rule like that. You don't have to write that down. I'm just saying you might have looked at the 30, 60, 90s in one of those ways, kind of depending on your teacher or how exactly they formulate or give you, formulaic, made a formula. How about that? You would have treated it something like that. Let's go ahead and apply it to a couple problems. Solve the missing sides. Okay, we'll go an easy one. Okay, we've got that side of 5. What would the hypotenuse be? Hypotenuse 10. Hypotenuse would be 10. So it's twice as long as the short leg. What would the long leg be? 5 square roots of 3. What if I gave you this triangle? So I gave you the hypotenuse, so then I would want to find the short leg first. What would the short leg be? 3.5, but I don't really like decimal form. I'd rather have fraction form and improper fraction with that. So I would just call it 7/2. 7/2. And if that's 7/2, what is the long leg? Be 7/2 times square root of 3. When you multiply by square root of 3, that's multiplying to the numerator, really. So I would write it as 7 square roots of 3/2. All right, how about this one? This one's a little bit more challenging. So I'm giving you the long leg. I would first want to find the short leg. How do you move from the long leg to the short leg? What do we have to do? Think about Think about, if you look at question number 1, the short leg was 5, the long leg was 5 square root of 3. Mathematically speaking, in terms of operations, what did I do to the 5 on number 1 to get to 5 square root of 3? I would have multiplied by square root of 3. So if I want to work backwards on number 3, what shall I do? Right? Divide by square root of 3, right? So what I'm going to do is take the long leg and divide it by square root of 3. What is 5 square root of 6 divided by square root of 3? And I don't want a decimal. I want to leave it in simplified radical form. So look at the square root of 6 over the square root of 3. What does square root of 6 over square root of 3 become? Square root of 2. They're both square roots, so you can simplify them. 6 over 3 goes to 2 over 1. I don't need the 1 in the bottom, so it's just 5 square roots of 2. Perfect. And then what is the hypotenuse? If the long or the short leg is 5 square roots of 2, what's the hypotenuse? 10 square roots. One more of these. I'm going to give you a long leg again. So that's usually the hardest. If I give you the long leg as 9, I'd want to find the short leg first. We have to approach it similar to what we did in the last problem. So I will take the 9 and I will divide it by the square root of 3. This time the square root of 3 doesn't simplify with something in the top. And we can't leave a square root in the denominator. We have to rationalize that. So we're going to have to multiply the top and the bottom both by the square root of 3. And now on the top we get 9 square roots of 3. In the bottom we get 3. Square root of 3 times square root of 3 is the square root of 9, which is just 3. Now can that simplify? 9 and 3 can simplify. Good. So we end up with 3 square roots of 3 over 1. So just 3 square roots of 3. Which means our hypotenuse is 6 square roots of 3. It's a little hard to read. Let me try that. Okay, there we go. What's our other special right triangle? You remember we had 30, 60, 90, and then what else? 45, 45, 90. What kind of triangle is a 45, 45, 90? It is isosceles. Good. Two of the angles are the same, which means the sides opposite them are also the same. So I wouldn't call it a short leg and a long leg this time because they're both the same. We could just call them legs. If I had a leg of X, what's the other leg going to be? X. What would the hypotenuse be? Well, we could do Pythagorean theorem, But does anybody remember? Yeah, that would be, yep, we can use that to figure it out, but I'm curious if anybody remembers it from last year from geometry. It's a square root of 2. It's x square root of 2. So if I did it in terms of number instead of x, we could say each leg is 1, the hypotenuse would be square root of 2. Or if we just wanted a rule, what do I do to the leg to get the hypotenuse? If I want to go from 1 to square root of 2, what do I actually do? Multiply, yeah. If we look at it this way, we have x for a leg, and this is x times square root of 2. So we just took the leg, and we multiplied it by the square root of 2. So there's like a rule or a formula you could follow. So let's try a couple of these. Yeah. If I gave you that triangle, do we know that's a 45, 45, 90 if I don't even mark 45s on there? What guarantees that it is a 45, 45, 90? I marked it as isosceles. We have a right angle and the two legs are congruent. That forces the angles to be the same. So they have to be 45s. So if I give you a leg of 6, what's the other leg? What's the hypotenuse? 6 square root 2. Does this triangle have to be a 45, 45, 90? I didn't mark it as two sides congruent. Yeah, so we got a right angle, but I marked the other angles as congruent, so they have to be 45s. Good. So if I say one of the legs is 6 square root of 2, the other leg has to be the same. What does the hypotenuse become? You would have to take the short leg, or the leg, sorry, times the square root of 2. Square root of 2 times square root of 2 is 2. So we really have 6 times 2, which is 12. All right, how about this one? I give you the hypotenuse of 9 square roots of 3. What's the leg? What do I do to solve for the leg? I have to divide it by what? Square root of 2. And remember the square root of 3, you might have saw that and felt like you could just drop it off and call it 9. The square root of 3 was a 30, 60, 90 thing, not a 45, 45, 90. So we have to divide that by square root of 2. Square root of 3 over square root of 2 does not simplify. So we have to rationalize that. Numerator becomes 9 square roots of 6. The denominator becomes 2. Does that simplify? Square root of 6 does not simplify. And 9 over 2 does not simplify. That would be your answer. Okay, that's really the extent of the notes for today. I'm going to scroll back up, zoom out a little bit so you can see those patterns and kind of leave you with that. But assignment-wise, I have a worksheet today over these special right triangles.